Hello, everyone. Good evening. My name is Jonah. I'm a principal software engineer at Intuit, and presenting with me today is Kranti Vikram, a staff software engineer at Intuit. And today, we're going to be talking about observability at scale, running OpenTelemetry across an enterprise. A look at Intuit's journey of adopting OpenTelemetry to power our distributed tracing and other observability solutions. First, let's take a look at the agenda for today's talk. First, we're going to be talking about the journey Intuit's had towards adopting OpenTelemetry and distributed tracing. We're really going to talk about kind of the state we were in about 18 to 24 months ago, the problems that our engineers and our on-call engineers were facing, the solutions that they were using, and really how adopting tools like OpenTelemetry, Jaeger, and other vendor tools has really enabled Intuit to solve some of those problems. From there, we'll go into collection and instrumentation of trace data. So we'll talk about how we've managed to collect all of the data from the services running at Intuit and how we instrumented those services in a pretty easy way so that they could collect trace data. Then we'll talk about some of the processors we've built on top of OpenTelemetry, specifically how we are able to extract metrics from our trace data. And finally, we'll talk about tracing's role in reducing MTTR and MTTD. That's mean time to repair and mean time to detect for our services. Okay, so first, let's look at kind of the state Intuit was in 18 to 24 months ago. We were in a state 18 to 24 months ago where not too far from where we are today, but we had services running in a huge polyglot environment. We had teams running services in Kubernetes in AWS. We had teams running just on bare metal EC2 instances. We had teams running serverless functions. We had teams running in an on-prem data center. And we had a variety of tools that these services and teams were interacting with. We had an Istio service mesh. We had DynamoDB resources, RDS resources, really a really truly polyglot stack. And our engineers, while this gave them a lot of flexibility, we started to notice some pretty common problems across teams. One of the biggest ones being that when teams were talking and communicating with other services, troubleshooting both latency issues and error issues became really difficult. We had several incidents where teams would jump on a call, and it was basically like dominoes trying to page the right on-call team. Team one would notice latency. They would get, onto some kind of virtual call, and then they would realize, oh no, it's team two. And then we would page team two, and then team two would be like, oh no, it's team three. And we just keep paging teams down the stack until we realized where the root cause was, because teams didn't have visibility past their own services. And the reason they didn't have this visibility is because we really didn't have the tool chain to actually identify what these dependencies were and how far they went. We had a very basic tracing mechanism. We had a header called Intuit_TID, which was Intuit Trace ID, which services generally propagated, not 100% coverage, but they were pretty good about propagating. But this header really didn't tell us anything about the relationships between services, other than that they both had a common API call. The only way you could use this header was searching in our log storage, and even then, you had to search across 3 or 4 different log indexes to actually be able to use that data. And that data still wasn't, it didn't solve for problems like asynchronous communication over a Kafka broker, or it didn't solve for clock skew between services, and it didn't have information about like parent-child relationships. So it was really, really hard to use that header to actually understand what dependencies between services were. This diagram really just shows kind of that state where we have all of these different application instances, maybe central services or services specific to like our QuickBooks platform, all pushing data to different log indexer and search tools. So the shared services would have their own instance of a log indexer. The QuickBooks services would have their own instances of a log indexer, and these instances weren't talking to each other. And it's the same story for like APM tools. Intuit leverages a tool called AppDynamics, and it was sort of the same story where these some of our services would push to one instance on the AppDynamics SaaS platform, and other services would push to a second instance. and these instances couldn't talk to each other. So none of this correlation data between services was actually visible in a core, like, single place. Developers had to go through multiple tools, multiple log instances, multiple APM tools, really to get a sense of the system-wide health. They couldn't just go into one place and say, hey, for this request, these are all the services involved, these are the latency times that each of them spent, and it was a real problem, right? Engineers couldn't troubleshoot issues in just a minute or two. It often would take 20, 30 minutes just to understand how one certain API or request was working across the system. And some other problems that kind of, in the same area were that we didn't have a standard trace log format. That Intuit TID was really the only thing that was powering it, and nobody interopted with it. AppDynamics didn't understand it. New Relic wouldn't understand, and none of these solutions would go out there and understand what that header meant. We didn't have a single tracing solution across Intuit. Some teams had looked at different standards. Within small groups, teams might be using something like a Zipkin to actually trace the requests across their 3 or 4 services. But across the company, there was no single place that you could go and actually visualize a trace across all Intuit services involved in the request, which was a huge problem. And so, with these problems, we had a team get together and really think about, like, what is the right solution. We looked at the industry where they were at. There were a couple standards at the time that were competing. There was open tracing, there was OpenCensus. Both in the distributed tracing space, both had their own standards in terms of how to propagate data. And we looked at first attempting to build our own tracing library that kind of leveraged some of those standards to propagate information. Before we get into that, though, I want to talk about the role of observability in reducing those outages that we were talking about, or those incidents that we were talking about. Intuit, as a SaaS provider, has a pretty high standard for how much time that we want to spend during an incident down. Obviously, as little as possible. But in this case, we have a budget max across all services of around 22 minutes per month of downtime at most. And one of the things to highlight here is that budget isn't just for time to repair things, but it also includes time waiting for time to detect as well, waiting for alerts to go off, waiting for the on-call to join an incident call and page other people. So when we think about it, that 22 minutes is really almost no time at all. And so if we can bring that, any tooling that we can get that can help us improve the time to both detect and time to recover on an incident is something that Intuit is very interested in. And that's why we started looking at observability tools and in the distributed tracing space in general, was to solve both a better mean to time to detect and also help our engineers recover faster and be able to isolate the problem faster. Okay, so let's go into distributed tracing and kind of how that first distributed tracing library that Intuit worked on got us from a not so great state to an okay state. So if we look at the diagram at the left here, we're basically just showing a service diagram of 10 or 15 requests where it shows all of these requests coming in, all of these requests bouncing across different services. And it's really hard to follow which requests are actually going to which service. And this diagram is pretty representative of how it felt to be an Intuit engineer at the time, where you saw these requests come in. You had the links here, but it was really hard to follow the paths between these requests to actually understand the dependencies in these services. So when we rolled out our first tracing library, which was basically just a library that extended the Intuit TID header and added some span headers as well, a span being just a component, one part of a larger trace, we started to see that we could actually identify requests throughout the system and see where they started, see where they ended. And it was a little bit easier to search through the noise. We could see the path that an individual request was taking. And as we noticed this, as we discovered that, yes, distributed tracing actually is going to be very valuable to Intuit, we realized that we should invest heavily in it and actually start to adopt open standards instead. Okay, quick highlight of some of the terminology I'm mentioning here in terms of how distributed tracing systems generally work. There's 2 key concepts to understand here. There's the concept of a trace. So the trace in this diagram is every basically everything under this A block and including this A block. And all of those individual objects are called spans. And those spans are usually just single operations that are part of a trace. So if you want to think about it in terms of like an API call, let's say I'm making an API call to the Hacker News API. The single API call and everything that happened in it would be a trace. Each individual operation in that call, so any API gateway operations, any database operations, any business logic, all of those would be individual spans that ladder up to serving that API call. And so the way that these tools are actually, and these models are actually used, is that you have a request come into a microservice. That request is going to have some kind of trace data on it, maybe a trace header or maybe nothing at all. That microservice, when it calls other services or does other operations, is going to create those new span objects that we talked about. And those span objects are going to interact with some kind of local tracing API. So in our case, it's an open tracing API in the JVM typically. That tracing API is going to be configured to talk to some tracing library or tracing collector. And then that tracing collector is going to send data to a trace storage layer. And this is generally how you're going to see most tracing architectures work at a high level, is that they're going to have some kind of instrumentation on your app servers. That instrumentation is going to help facilitate the propagation of the required headers like trace IDs, span IDs, and then any like baggage between systems. And then all of these systems are going to independently report their view of the trace, so the spans that they generate, to that tracing API that they have, which is going to kind of send it to a collector, which will store it and normalize it so that when somebody wants to come and view it, they're able to use some trace visualization tool like Jaeger or Zipkin or any of the third-party vendors out there to actually reconstruct the full view of the trace and then do maybe analytics in terms of like generating metrics or things like that on it. So if we look at how we set this architecture up at Intuit, it basically follows that guide that we looked at before. So Intuit today has two primary ways of running services. We have services that run on Kubernetes. So they'll have multiple pods running a Kubernetes cluster, or we have services running on just pure EC2 on AWS. So they'll have a AMI that they use. They will start their server, and they might have one or several daemons running on that. And so for both of those cases today, we run an OpenTelemetry agent, which is just basically a configured container using the open source OpenTelemetry agent container that has configuration to send to a AWS private link endpoint. So anytime a new node joins our Kubernetes cluster, we've got a Kubernetes daemon set in place that will automatically provision an OpenTelemetry agent. That OpenTelemetry agent is automatically configured to use gRPC with an AWS private link endpoint that's automatically configured in that account to talk to a central collector tier. And it's the same thing on our EC2 instances today. When you provision a new EC2 instance using the Intuit-based AMI, there's a daemon already pre-configured. You just have to run like a service.start on that daemon. And that daemon is basically going to auto-discover that AWS private link endpoint. And again, it's going to use gRPC to communicate from the agent to the OpenTelemetry collector node. Now, those collector nodes are typically running in the same AWS region. So if you're running in a US West 2 region, there will be a collector tier in US West 2 to receive those trace data. And the same goes for any other region that Intuit operates in. So any major AWS region, we have a collector tier set up to kind of collect all of that data. And from there, that OpenTelemetry collector tier uses gRPC and Envoy to basically push that data to a Jaeger collector tier. Initially, it was a separate tier, but the Jaeger team has actually been working to consolidate a lot of that into the OpenTelemetry community as well, in terms of extra receivers, extra processors, extra exporters. And so that's actually really becoming a consolidated tier today. And then from there, data goes to a trace storage system, in our case, AWS ElasticSearch. And from there, it goes to a Jaeger user interface where engineers can search for traces based on different tags, based on the trace ID, things like that. and it'll give them a pretty solid view of the trace. And with that, I'm going to hand it over to Kranti.
Thank you, Jonah. As Jonah mentioned in one of his initial slides, for Intuit product to serve a single user or API request, hundreds of services are invoked behind the scene to compose its response. These services are often owned by different teams or are from different functional groups. So when a customer complains about a slowness in your application or an alarm is triggered for the same, there are some common questions that pop up. Which flow or which request had issues? Is one of my components having an issue? Or is it one of the dependent service that's having an issue? Is the dependent service throwing an error? Or is it the high latency of the dependent service that's causing this repercussion? Typically, in such cases, what do? We take the time window and dig through the logs to find something useful. We also pull in teams from different services to troubleshoot this issue. This process is very time consuming, involves many people, and often we don't find the root cause of the issue. So whom do we blame if we don't find the root cause? We blame it on the network. Distributed tracing helps in addressing this issue. It is a process of tracking a request end to end as it traverses through multiple services in near real time. So let's see it in action. We have 3 microservices handling a retail order. All these 3 microservices are instrumented with OpenTracing or OpenTelemetry libraries. When a retail order is placed, a trace context gets created and also generates a server span, which would have trace ID to identify a distributed transaction, a span ID to identify the transaction flow within the order service, a parent span ID to identify the span that initiated this transaction. Since order service is a edge service or the first service receiving the request, the parent ID would be null. Now, when a downstream call is made, a similar span gets created, but with the parent ID being same as the span ID of the order service. The same happens with the billing service. Now, when the billing service responds back to the allocation services request, a client span gets created. So the spans continue to get created in this fashion. So once we have all these spans, we could definitely visualize this in a timeline view with a parent-child relationship. And the spans have rich information such as the status code of the request, the latency, and some custom tags that would help to filter these spans from the trace store. So these spans later get shipped to the OpenTelemetry collector and they end up in the trace store. So we can build a lot of analytics and visualization pieces to get insights from this stored data. So one key thing to note here is that OpenTelemetry collector becomes our tracing backend abstraction layer. It can accept spans in different formats, and it can spit out spans in a desired format. Let's look at metrics. There are a lot of different types of metrics that you can capture for your system, starting with system resource metrics, CPU, memory for your pod or node. There are a bunch of AWS resource metrics, CloudWatch metrics coming from ElasticSearch, DynamoDB, RDS, serverless, so on and so forth. And we also have transaction metrics. These are the metrics that give you insights on the API's request rate, error rate, duration, or at the service level as well. So these are the transaction metrics. Today we will talk about red metrics, the problem we had, and how we solved it using a streaming pipeline. So in the initial solution, services were pushing logs with latency and status code. We had scheduled queries on top of our log management system. Queries used to run every minute and push those to S3 bucket. And we had a Lambda which pushed the data to our time series DB. Everybody liked it and started pushing more and more data. We soon had thousands of queries running and competing for each other. We had delays in metrics. We made queries run every 10 minutes to mitigate this issue. We found that traces or spans had these details. The details that I'm talking about is the status code, the response time, the service name, the API name, so on and so forth. Each span had these details in a consistent format. We knew that we could take advantage of this. So we enhanced the OpenTelemetry collector to extract metrics from spans as they flow through the collector to the tracing backend. So the metrics extracted by the OpenTelemetry collector were then streamed to metrics aggregator to summarize the metrics and then push them to our time series database. This brought in a couple of advantages or benefits. Definitely one of the benefit was the metrics were available to us in less than a minute when compared with 10 minutes to the earlier solution. So the top three graphs represent the data coming out of our previous log-based pipeline. Bottom three show data coming from our observability pipeline. First, on the top leftmost graph shows TPS numbers, shows dots that are separated by 10 minutes or more than that. On the bottom, you see it's coming every minute or even every 30 seconds. Second graph shows the error rate. You can see dotted lines. That means we did not get any data at that period of time. That means we were flying blind during that period of time. Whereas our new observability pipeline is showing continuous metrics. Definitely we saw 10 minutes reduction in our mean time to detect because of this new pipeline. So let's get into the benefits of traces and trace metrics. Topology view helps in quickly identifying a faulty service. Autocorrelation helps to identify the impacted API and root cause quickly. Not just for identifying issues, traces and trace metrics also help in running performance analysis on pre-prod or prod deployments. So we could analyze the aggregated TPS, TP metrics at service and API level, enabling comparison between current and past baselines, help in deployment regressions and canary rollouts. Time for Q&A.